Okay, so I've been playing a little bit loose with language here because we defined the concept of independence of two events, but here I have been referring to independent coin tosses where I'm thinking about many coin tosses, like 10 or 11 of them. So to be proper, I should have defined for you also the notion of independence of multiple events, not just two. We don't want to just say coin toss 1 is independent from coin toss 2. We want to be able to say something like these 10 coin tosses are all independent of each other. Intuitively, what that means should be the same thing, that information about some of the coin tosses doesn't change your beliefs about the remaining coin tosses. How do we translate that into a mathematical definition? Well, an ugly attempt would be to impose requirements such as this. Think of A1 being the event that the first flip was heads, A2 is the event that the second flip was heads, A3 that the third flip was heads, and so on. Here's an event whose occurrence or not is determined by the first 3 coin flips. And here's an event whose occurrence or not is determined by the 5th and 6th coin flip. If we think physically that all those coin flips have nothing to do with each other, information about the 5th and 6th coin flip are not going to change what we expect from the first 3. So the probability of this event, the conditional probability, should be the same as the unconditional probability. And we would like a relation of this kind to be true no matter what kind of formula you write down, as long as the events that show up here are different from the events that show up there. Okay, that's sort of an ugly definition. The mathematical definition that actually does the job and leads to all formulas of this kind is the following. We're going to say that a collection of events are independent if we can find the probability of their joint occurrence by just multiplying probabilities. And that will be true even if you look at sub-collections of these events. Let's make that more precise. If we have 3 events, the definition tells us that the 3 events are independent if the following are true. Probability A1 and A2 and A3. You can calculate this probability by multiplying individual probabilities. But the same is true even if you take fewer events, just a few indices out of the indices that we have available. So we also require PA1 intersection A2 is PA1 times PA2. And similarly for the other possibilities of choosing the indices. Okay, so independence, mathematical definition, requires that calculating probabilities of any intersection of the events we have in our hands, that calculation can be done by just multiplying individual probabilities. And this has to apply to the case where we consider all of the events in our hands or just sub-collections of those events. Now, these relations, just by themselves, are called pairwise independence. So this relation, for example, tells us that A1 is independent from A2. This tells us that A2 is independent from A3. This will tell us that A1 is independent from A3. But independence of all the events together actually requires a little more, one more equality that has to do with all 3 events being considered at the same time. And this extra equality is not redundant. It actually does make a difference. Independence and pairwise independence are different things.